Assalamualaikum and good day. I'm Dr. Jahariah Sampe from Universiti Kebangsaan Malaysia, Institute of Microengineering and Nanoelectronics, or IMEN. Today I will present our research work on digital phase frequency detector in all digital phase loop or PLL based local oscillator for radio frequency identifications or RFID system transceiver. So this is my presentation's outline. We'll start with the introductions and then overview, objective, our proposed architecture, simulations, result, and end up with the conclusions. So as an introductions, radio frequency identifications or RFID system had been developed and extensively deployed in the healthcare and biomedical applications, and the RFID system goal is to transfer identification data between this tag and this RFID and through the RF transceiver to conduct a certain applications based on the data stored in this tag. So this RFID system consists of RF reader, tag, and the processing unit here. So for the transceiver, there are 5 important blocks: antenna, receiver transceiver switch, receiver block, transmitter block, and also local oscillator. So this local oscillator is important component in order to generate selected frequency for this transmitter and this receiver in this transceiver. So however our target application is for 2.4 gigahertz applications. So we need to have a frequency synthesizer, so to generate a variable high frequency for this local oscillator. Traditionally, the frequency synthesizer is developed in analog based loop or PLL configurations, but with the advancement of CMOS technology, all the digital PLL or ADPLL get more attention due to its excellent performance in terms of low power consumption, a small size, fast-paced frequency detections, fast locking time, increased stability, and better jitter performance. This is the overview of the all digital PLL. Consists of a digital phase frequency detector, control unit, digital control oscillator or DCO, and divider here. There are 2 input here involve reference signal and also feedback signal, and the DCO signal, the output is the DCO signal. So this configurations is similar to the analog PLL, but the circuitry in this ADPLL is all in digital format. So the digital PFD here detect the difference and mismatch of the phase or frequency input signal here, which is reference and feedback signals. And the control unit here is to adjust and control the digital code for the DCO according to this input signal up and down. And digital control oscillator here to perform the frequency variations for the ADPL output signal. And the divider here is to reduce the frequency of this DCO before feedback to the DPFD block. So nowadays, researchers are focused on the digital PFD designed to perform a fast acquisition performance, and the most popular method is using the time to digital converter or TDC. So this TDC actually well functions to measure and estimate the time difference between the positive or negative edge of these 2 input signals. However, use of full range of TDC will consume high power and degrade the performance of ADPLL. Therefore, our research objective here to develop an architecture of digital phase frequency detector with a fast acquisition step by using a phase detection sequential state machine and comparator-based frequency detector. So this is our proposed architecture for the phase frequency detector. Consists of phase detector and frequency detector. Involve two input signal, clock reference and clock feedback. The phase detector output is up and down, and frequency detector output is fast, slow and equal. So this is the operations of our phase detector. At the beginning, state 0 here, so both output are 0, 0, and at state 1 occur when the positive edge of the clock reference signal, and during this stage, the up signal become 1 and down remain 0. So here also the clock reference will lead the clock feedback in terms of pace. So the PD will remain in this stage 1 until a positive edge signal of clock feedback is detected. So the PD will immediately perform a state 3, where in this state 3 up and down are 1. And at these conditions, the PD under reset conditions and then restore back to the state 0. So state 2 occur when the positive edge of clock feedback, and during this state, the down output will 1 and up output will 0. And here during this stage, the clock feedback will lead the clock reference in terms of pace, and the PD operations of this state 2 will remain until a positive edge of clock reference is detected, and the PD will immediately perform a state 3. So this is our proposed phase detector. Actually, here we simulate our PD using two software, MATLAB and Verilog, because we want to see the performance between these two software. And then the difference here, using MATLAB, we need to insert a delay here, but in Verilog no need to insert any delay. So for the frequency detector design, the two input signal are clock reference and clock FB, and we produce three output signal, equal, fast and slow. And in this FD, there are two main parts. One is two counter are used for counting the reference signal cycle, and the other is to count a feedback signal cycle. And a comparator is used to compare the output of these two counter and produce three output signal of fast, slow and equal. So the target of the proposed FD is to enable the operations of DCO in our future design. And here equal will represent FD need to send a signal to maintain the frequency. Fast means FD need to send a signal to speed up the DCO frequency, and slow means that FD need to send signal to slow down the DCO frequency. So this is the operations of our frequency detector based on this flow chart. And initially all the variable are set to 0 and the input clock reference and clock bit are counting until the 10th cycle, and after the 10th cycle is completed, so the comparison will be made here. If the clock's reference is equal to clock FB, so the output signal of equal will be triggered. But if both completed signal do not equal, so the comparison need to be redo again. So if the completed signal of clock reference arrive first, so the first output signal will be triggered, and if the completed signal of clock feedback arrive first, so the slow output signal will be triggered. So this is our frequency detector design in Verilog. And for the simulation result in PES detector, we try to design our architecture using MATLAB and also Verilog, and we compare the performance, and we found out that in MATLAB we need to add a delay element in order to composite with the date zone. So this will increase the delay in MATLAB as compared to in Verilog. Where in Verilog there is no delay element because we design the architecture using according to the positive or negative edge trigger clock. So this is the simulation result of the PES detector using MATLAB for step 0, 1 and 2. And this is the simulation result using Verilog for the PES detector. This is step 0, 1 and 2. From these two output simulations, we measure the difference between two input signal of clock reference and feedback reference, and we find out that in MATLAB the difference is very high, which is equal to 200 picosecond, and in Verilog only 3 picosecond. So this is due to the delay that we need to insert in the MATLAB due to the to composite the date zone. So from that time difference, we can calculate the duty cycle for each for the up and down signal for the using MATLAB and also using a Verilog, and of course a duty cycle for this for the Verilog is much smaller, which is equal to 1.7. So in the frequency detector design, we will have two input signal, clock feedback and also reference feedback clock and also reference clock, and there are three output signal, equal, fast and slow, and then the completed count is triggered when the clock reference and clock feedback are completed count of 10 cycle. So the past position of the complete count for both signal is compared below. So if equal means complete reference equal to complete feedback signal, and fast means complete reference faster than complete feedback, and slow means complete reference slower than complete feedback. So this is the simulation result for the for the frequency detector. This is for equal. This is for equal output. This is for slow output, and this is for fast output. And as a conclusion, the digital PFD is designed and simulated using better simulator and Verilog, because we already test the design of PES detector using MATLAB and Verilog, where MATLAB will give very long time difference because of we need to insert the delay element in the design to composite the dead zone. And here we can calculate the time difference between using MATLAB and Verilog is the 3 picosecond and 200 picosecond respectively. And also we also design our frequency detector using a frequency comparison technique in Verilog, and this PES detector will produce 3 output signal of fast, slow and equal. And for future work, the output signal generated for this proposed PD and FD will be connected to the control unit of the ADPLL frequency synthesizer for RFID applications by using Verilog. So this is our reference. This is among our reference. This is our publications, which is review paper. And thank you very much for your attention. Any questions?